introductory portion of inductors by looking at them in DC and AC circuits. So let's go ahead and recap last time. So last time we introduced, oops, sorry, that should be a subscript, not minus. Also, it should be a lowercase b. Right, we had our equation for our voltage across an inductor. It's going to be equal to the inductance times the current, but it is the time derivative of the current that we are going to be having for this. We looked at inductors in series and in parallel because of how voltage and current are related to inductance. It matches the same way that we have it for resistors. This is why their equations for series and parallel look similar. Any questions about last time? Today we're going to look at inductors in DC and AC circuits, focusing more so on the DC portion of it. We will again come back to this next week where we look at a lot of this in more detail. So if we think about the equation that we had for voltage, right, that was related to the time derivative of the current. So when current is constant, there is no induced voltage across our inductor. What does this look similar to? We have no change in voltage over our circuit. What? Is not going to be something in parallel. Charged capacitors definitely have a voltage.
Well, I mean, it's not. Oh, I think no.
No voltage at all. Yes.
An ideal wire.
An ideal wire. So when the current is constant, and this is something that'll pop up a couple more times just so we make sure we understand that. When the current is constant, there is no induced voltage. Our inductor will act as an ideal wire. So it's only when we have changing current where we're going to actually have some voltage across our inductor. So it appears like a short, or again, an ideal wire. So we have a time constant for when we have resistors and inductors inside of the same circuit. The equation is going to be different, but it is still represented with tau. So now for an RL circuit, tau is going to be equal to the inductance divided by the resistance value. Its SI unit is still going to be seconds. So we're not going to do the unit proof. It is in the textbook if you want to see it. So why might I care about a time constant for an inductor circuit? Yeah, so, right, we had the time constant, in particular 5 tau was a long time for the RC circuit. It's also going to be true where 5 tau is a long time according to the RL circuit. And so that will help us figure out when do we have our maximum or minimum current values. Why else might we want this? It's so some equations look the same regardless of what type of circuit that we have, and we'll show that on the next slide.
Constant and stuff.
What do you mean?
How long it take to charge? I don't remember.
So for the time constant for an RC circuit was relating to charging. For the RL circuit, it's going to be related to the value of the current, more so than the voltage. So if we have our resistor and inductor in series, this is typically going to be what we have for this particular lecture. Same rules apply to anything else that was in series. They will have the same current values. So because they have the same current, right, we can go through and we would be able to see what that happens to look like. So in this bottom image here, we have the current as a function of time. And we can see once again that once we reach 5 tau, this is close enough to us being at 100%. It's like 99.5, I think 2% is what it's at. Close enough for us. So this will get us from no current to the maximum possible current that we have in our inductor, which because it's in series will be the same as our resistor. So we can find this final current value by utilizing Ohm's law. So here we have IF is equal to VS divided by R. Why do I not need to include the inductor for the maximum current value here?
You're not determine the maximum current without it.
But why?
It's Ohm's law.
No, not because it's Ohm's law. Why can't I use Ohm's law?
So we don't need the inductance or whatever.
You don't need to include the inductor in finding the final or the maximum current value. Yes.
I think you got it because
Yeah.
the maximum's not gonna change, so we treat it as if it's static. But we're doing the equation, which allows us to use Ohm's law.
So, but the reason it's considered maximum is because that is where we're going to have a change in voltage across the inductor is 0. So that is where we have reached the point where we're at the maximum. It's not changing. We now have an ideal wire for our inductor. And so only the resistor is going to affect the voltage value or sorry, affect the current value. Yes.
Inductor rates the
Mhm.
and reverse voltage,
Yes.
like equal, like are they related? Like through Ohm's law.
So this current here is the current inside of the circuit. We'll see the equations for the current of the inductor, I think on the next slide.
That's
But eventually,
slowly, or it's quickly
Yeah.
going away
because you're no longer changing the current.
because
Yeah, the current inside of the circuit no longer changes. So the voltage will drop off across the inductor and the current will go to its maximum. Yeah. The same thing is true for going through and doing the other way where if we are having it go down to 0. So this here, we'll focus more on this behavior next week when we go through and look at the RL circuit in a lot more detail. But with this behavior here, we're still having that exponential increase and decrease, and we are still calling 5 tau long time to go through and have our maximum, or in the case on the right side, go from maximum to 0 for the current. So in reality, with a DC source, there's not much interesting in stuff that we can do with an inductor because It's just gonna slowly phase out with going through and having it. So it's only once we get into the LC circuit or the LRC circuit where we're going to start getting a lot more interesting behaviors because we'll start having alternating sources. So the alternating current stuff also is a little bit more interesting with that. So we'll touch a little bit on the AC stuff, but we'll come back to it in a lot more detail. I want to say the week before Thanksgiving. Any questions so far about an inductor in a DC circuit? So let's consider a square wave. I know realistically the square wave is not real, but it's very nice for going through and showing the behaviors that we have for our inductor. So here we have a situation where we are going to have a square wave come in, and we want to look at how the voltage and the current changes across this particular inductor. So let's say, right, we have it's at 0, and then we turn on our source. With this here, this is kind of the most interesting type of DC source that we're going to have because it is technically alternating, but we have these flat plateaus at the top portion, and that is corresponding to roughly what a DC looks like. So for the response of the inductor, right, it opposes any change that we have in current. So that means that if I am to increase my current, should the induced current of the inductor point in the same or opposite direction? By the opposite. Yeah, so it's going to oppose it. When I decrease the current, will it point in the same or opposite? Will not point in the opposite direction because it wants to keep the value as close to the same numerical value as possible. So if I'm decreasing the current, it will point in the same direction to try to keep that total current value the same. I put that box in the wrong spot. So we'll skip along real quick. All right, so here we have the voltage of the source, and we have the voltage of the inductor, both plotted. So this is voltage, not current. Or
This says that the current increases the induced.
oh, oops. Yeah, I copied sentence, yeah. Yeah. Yeah, I copied a sentence because I don't want to type it all out. So I copied one. So let's look at these graphs here. So if we look at our voltage situation, right, this is our square wave. So it's going to, according to time, right, it's nothing, nothing, nothing. It jumps up to some specific value. It's going to hold it for some amount of time, and then it's going to drop back down to 0. If we look at our response for our voltage for the inductor, that's what this bottom one here is. The only way we can tell the difference is this one says the S and this one says the L. Right? It's going to be nothing while there's no change in the voltage from our source. As we go through, there is a little bit of a change in the voltage as we jump up. Right? It's going in the opposite direction because we want to induce a current that counteracts the direction of the current that is being supplied by the source. As we hold it constant, what's going to happen is it's going to fall off, or it's going to go back to 0 because, right, it's some amount of time has passed. And so you're going to keep that current steady. It is going to go back to having 0 voltage. And then when we switch it again, it once again goes through and has that fluctuation in the voltage value. If you had to get, I want you to discuss with your neighbors, how would you go through and draw the current for the, this type of graph here, right? This is voltage. How would we go through and look at the current through it?
You know, you should just do the equation, get so many points in approximate. I think you're right. Petitioning. Much my computer. Andrew knows from me. Partition review. So the dot's now gone. Then I'm going to reduce the size, but to reduce the size of my current partitions, I have to fly boot to another system. So technically it's running. We don't want to start changing.
So none of you had drawn a graph, so I'm going to make you trace it out in the air for me. Roughly, what do you think this graph should look like?
That's what I was thinking was similar to the voltage.
Okay, so when you say backwards, do you mean
Like,
positive?
Mm-hmm.
no,
Okay, so voltage goes up, current's gonna be very low.
So you think it'll go small to large?
Yeah,
So
yeah,
that,
yeah.
I just think the first half of the voltage is.
Yeah, just like you.
and you think, you see that?
The other way, I think the other half is just gonna repeat that.
Yeah.
Yeah, it's gonna match it.
Okay. So if I'm being honest, this image is from a different example, same general idea though. It looks something like this.
It goes negative. That current? Yep.
Yes. This is one that has numerical values with it, so I cropped it to take off the numbers. So let's talk about what's going on with it. Again, this isn't for this particular one. This is with one of the examples that I recommend you go through and look at. So this is an example of what the current can look like. So it'll, right. So let me double check which example that is, really quick. I don't want to accidentally lie to you about which one this is. So this one is, if we go to chapter 13, section 4. Make this big enough that I can actually read it. This one here is for example, this is for example 13.8. Or no, not 13.8. Sorry, 13.9. No, where's this image from? Okay. So this is from 13.11. So example 13.11. So for this one, we're using the equation I keep thinking is on the next slide. It'll show up eventually for going through and doing this. But with it, it is responding to a similar square wave. So what's going to happen is it's going to, right, with this decreasing part here, this is going to be where we're keeping this flat. Right, it's constant. It's going to go down back to 0 where it becomes like an ideal wire. So this here is the current in the inductor. So that's what this part here is. It takes a short amount of time for it to get up to that value, but then it's going to go back down 0. Yes. It does look similar, but that's only going to be because in this case, the voltage is and the current are a lot easier to connect to each other because it's just an inductor and a capacitor. That will not always be, so yeah, the resistor. Once we add the capacitor, that's not necessarily going to be the case. Yes, it does look like the derivative because of how you could go through and connect the current and the voltage from the source. So behold, actually having the equations. So what these equations look like? The top one here, right? This is our instantaneous voltage, and why they look familiar? What do they look like to you?
Like the capacitor.
Yeah. This looks like the capacitor one. That's because, and this is one of the reasons why we want to keep seeing tau brought up for this type of circuit, because if we're using the time constant, we can start with the same starting equation for the RL or the RC circuit. These are the same equations because we're using tau. If we don't use tau, right, they're going to look a little bit different, where one's going to have RC in the denominator, the other one should be R times L, or RT divided by L. So with this equation here, again, these are the generalized forms. So this will be something that you are given on a quiz or an exam. With this here, though, what we tend to focus on is a little bit different. For the RC circuit, we almost exclusively are going to be dealing with the voltage part because we're looking at building up charge or taking away charge on our capacitor, which is related to the voltage. For the inductor, more often we are concerned with the current portion of it. So typically which one we focus on is going to be a little bit different. So for this one here, we want to go through and do a similar analysis of thinking about when we're changing, but here we're going to look at the changing current. How does it look like for increasing and for decreasing current? It is going to be given where the initial current value is going to be equal to 0. We have a 0 here. We can go through and rewrite this out by having 1 minus e to the negative t divided by tau times the final value. Or again, this final value, we're going to go through and solve using Ohm's law, where the inductance is acting at, or the inductor is acting as an ideal wire. So if we're decreasing, that's going to be the situation where our final current is going to be 0. So that whole stuff is 0, and all we're going to have is the initial current e to the minus t divided by tau. We just need to be careful, again, knowing with initial and finals what those look like, going through and utilizing it. Any questions on inductors so far? Yes. Yeah. Typically, the square wave does not go negative. Yes, it's more so looks like a bunch of square pulses. If it's that one has a different name and I can't remember what it is off the top of my head.
Big drop
Mm-hmm.
used by the inductor being twice as high. So that it's not produce like 10 volts, even if it's a 5 volt AC.
You're having a 10 volt
Yeah.
across that. So this is why typically we only look at the top part of it. Inductor. Mm-hmm. These are the inductor values. Yes.
So in the same way for capacitors where the current can limit it, I assume the voltage also at extreme scenarios can limit the inductors.
Yes. There's a lot of weird things with large voltages that can happen, or large changes with circuits that can affect the inductor. So I think with inductors, we want to be careful. We always want to talk about it being a change, because if there's no change, then it just is there, not really doing anything. Any other questions so far? So we are going to work our way through 29 and 30. So for 29 here, we are going to solve for the time constant of the circuit. So the inductance part of it's pretty easy. We only have one. Question is going to be, how do we take all these resistors and put them into a single resistance value? Because in this case, when we're looking at tau, it's going to be inductance times the total, or sorry, not, that's not, nope, ignore that. All divided by RT. So how do we find RT? And feel free to discuss with your neighbors, how do we go through and do that? Yes.
Like, what's that weird resistance we learned about like how it like a capacitor has is that
Inductance.
what was the type of resistance?
Oh, the reactance?
Yeah. Does that have reactance?
No, because this is a DC source. Reactance is only for AC.
Oh yeah.
Mhm.
But if it wasn't AC,
If it was AC, then this question gets easier.
what would we need to figure out the reactance?
We don't. Nope, we don't need to.
You see that? You use a button to get gas.
Yeah, it's just one or two.
It's like if you're just
Right.
Would be all the resistors. Eight. I don't know. The previous or yeah. It's like. That's. Whatever this is. Yeah.
And I'm doing.
No,
I did not. So what did you? Like.
Either there.
All right, how did you guys go through and start figuring out RT? You have to Thevenize it. Yeah, it's fine. I also can't spell it to save my life unless it's written out in front of me. So, you know. All right, so if we're going to Thevenize this circuit, how are we going to go through and do that, Maddox? What'd you do? So certain this should be -1, not +1. So this is going to be how we go through and find RT. So we can redraw this. Right, and here we'll have this part and this part. So we have the two sections in parallel. If we have the ideal wire situation, either then in series, so RT is going to be this. So we'll have 1 over 4.7 times 10 to the 3 plus 1 over 4.7 times 10 to the 3 inversed plus 1 over 3.8 times 10 to the 3 plus 1 over 6.8 times 10 to the 3 to the -1. And so now that we have this, we can find tau, and assuming I plugged this in correctly, I got 7.2182 times 10 to the -7 seconds. Or if we wanted to go through and round this, tau is equal to 7.22 times 10 to the -7 seconds, or 0.722 milliseconds, or microns. Questions on 29 before we use this for 30? Yes.
So you replace the L1 touch wire.
So you're talking about for when you do the
Yeah.
Thevenizing? That is where you're trying to look at the voltage. So yes.
That
Yes.
out.
Yeah.
and see what the other ones
Mm-hmm.
are. I just R2, 1 over R. No, R2 plus R4 is parallel with it.
Because of how it's connected to the source. So you can't just ignore the fact that the source is there. Unfortunately. Otherwise it would be a lot easier.
So you're starting from both ends.
Kinda, yeah.
And then you're going to the source back to the.
Mm-hmm. Yeah. All right. So we're gonna come back to this circuit here in a little bit because we will want to revisit it. So for 30A, we're finding the current in the inductor 1 micron after the switch closes. And for B, which I think B is going to be easier to solve first in comparison to A, is what is the current after 5 tau has elapsed. So this is the total current value. And so what we need to think about, right, we're going to have I is equal to V over RT. We already know RT, right? If we go through and look at this here, I plugged it in like this. I'm just going to write out what RT is in terms of numerical values. And find it again. So RT is going to be 2.35 times 10 to the 3 ohms plus 2.2278 times 10 to the 3 ohms. Those are the two sets in parallel and what they sum up to, so we can add those, and that's going to be RT. When doing our Thevenizing our circuit, there's one other thing that happens to our circuit besides having 2 new resistors. So this circuit here isn't quite a complete picture. When we go through and did our stuff for Thevian's, process and stuff, what did we also typically have? The new voltage. So, right, if we're going through and doing the new voltage, right, it's going to be here. It turns out it points the opposite direction. And it is going to have a value of 10.1 volts. This side keeping the 7.5 volts. I am not going to give you a question that makes you do this. Just showing you that this textbook's going to keep bringing it up anytime you have the Wheatstone looking situation. Yes.
So that 2.1.
It'd be the 10.1 minus the 7.5 because they're pointing opposite directions. So the real equivalent value is right 2.6 for going through and doing that. But if we add to the drawing that we have here, it looks like this. So that means that V here is going to be our 10.1 minus the 7.5. So those are just coming from the fact that when we're going through and doing this, we kind of basically are doing this part is one, we're kind of setting this twice, so we have the one over here and the one over here for going through and doing it. If we were to combine it all into one go, we'd have one resistor, which has the RT value, and one voltage value, which would be this here. So just going to go through and write that in. So assuming I went through and plugged this in correctly, I got that my total current value is going to be 5.6871 times 10 to the negative 4 amps. For B, because this is technically what we're solving for here, we should also go through and round it. We'll have 5.69 times 10 to the negative 4 amps, or if we wanted to, 0.569 milliamps. So for this current here, right, this is the initial or final current value. It's going to be the final value. And this is going to be the final value I'm able to go through and plug into 30A here. Because for this one, we're going to have I is equal to IF, 1 minus e to the negative t divided by tau. Why am I using this equation? Yeah, but why this one and not the one where it's I e to the negative t divided by tau? How do we know the initial current 0? What gives that away? Yeah, so the switch is open. So 29, right, says determine the time constant for the circuit. The switch is going to close, and then some amount of time is going to pass. So we are increasing the value. So we're going to be able to use the IF that we technically solved for in B because we did this out of order. Right, that was the 5.6871 times 10 to the negative 4 amps. 1 minus E. So here, my time is given in microns, so microseconds. I have a choice. When I calculated tau here, I did it in seconds, which was this numerical value here. I also went through, and because it's 10 to the negative 7, the closest thing we have to that is our microns. So we can choose convert the time given into seconds, or take our answer from 29 and use the mu-s version of it. Both will mathematically get you to the same point. It doesn't matter. Personally, I hate writing e to this whatever with more powers in there, so I like to use the mu values for doing this. If we do it, we want to make sure we are carrying those extra sig figs. So don't just use this answer here. We should use 2 to 3 extra digits for going through and solving for that. So I personally like this version a little bit more. Oops, sorry, 721. 2. So I personally, like I said, I personally like this more because that way I don't have times 10 to the negative 6 and times 10 to the negative 7 in there. You're welcome to do it whatever way you want. If we take this and plug it in, I got 1.4231 times 10 to the negative 4 amps, or the current 1 times 10 to the negative 6 seconds after the switch closes is 1.42 times 10 to the negative 4 amps, or 0.142 milliamps. Any questions about 29 or 30? It is possible I plugged it in wrong. So is your tau the same?
Yeah.
Okay, so it's, what'd you guys end up getting?
We got 0.4264 milliamps. The
That-
final we got was 0.56870 milliamps. Yeah,
So
and our signs are right, because I have,
B, but you have the same B. Or do you have different Bs? Okay, so it's just, I probably just plugged it in wrong. So this is the number you have though, correct? Okay. Yeah, I probably just plugged it in wrong because I was rushing. With doing that.
We, whatever, that make higher inductance make it take longer to charge,
Mhm.
or to not charge, like.
Yeah.
Yeah.
Yeah, because if we look at tau, right, it's L divided by R.
Yeah.
So the larger the inductance, the larger the tau value is going to be. Any other questions or comments about 29 and 30? So we're going to go through them and we're just going to talk about the phase relationship for current and voltage in an inductor. This here is for AC. So this is our equation that we have for the voltage, right? It is the time derivative, or the inductance times the time derivative of the current. Most of our AC sources, if we look at it, had the equation where the current was equal to IP. What did that stand for? What's IP stand for? That's going to be the peak or the maximum current, sine of 2 pi frequency times T. What is frequency in general? It's what per second? Yeah. It's technically oscillations per second. Because if you do periods per second, that's a unitless value. So if this here is our sine, right, is our current, when we take the time derivative of sine, what do we get? So we'll have a cosine, you'll have some other, right, chain rule stuff that pops out, which will change the scale. So when di over dt is a positive going maximum, the voltage across the inductor is also positive, is that positive maximum? If it's a negative going maximum, so it's negative sign. Right, we have a negative maximum. Right, it is just the sine or the cosine for it. So here we see that when we have zero current from our AC source, we are going to have the maximum voltage across our inductor. This is because we're going from negative towards positive. That is the steepest slope location. When we have, right, at our peak, so either the positive or the negative peak, right, we're changing directions. That is at that explicit instant in time, it's constant. That's why we have a zero value for our voltage there. So going to have that cosine graph that's going to be related to the voltage across the inductor. And again, right, there are those other right, with the chain rule, you'll have IP 2 pi frequency that we just typically call VL numerically. Right, so if we're looking at it, right, VL is equal to IP 2 pi frequency. Questions so far about the AC inductor stuff? So again, we need to just be careful with how the question is going to be worded for going through and figuring out if it's positive or negative sign. If we have a phase constant in there, how does that affect the derivative? A phase constant, the phi value. So we're not starting exactly at sign. So yeah, it's not going to change the magnitude, but it'll change the cosine function and the cosine function only. I just realized that there's something right there, so I'll have to move this. So this is what the phasor is going to look like. So here, the pinkish line that's pointing in the negative y direction, that is the current in the inductor, and then VL is going to be its voltage. There's a difference of 90 degrees between them. We'll focus more on phasors next week. They're just current and the voltage are out of phase with each other by 90 degrees. All right, so with inductive reactance, it is going to have a different equation. So if we look at our equation here relating voltage and the current value, we can also combine this with Ohm's law to go through and get that our inductance, our inductive reactance, so our XL, is going to be 2 pi times the frequency times that inductance value. So I'm going to have this again. This here is measured in ohms. What's the inverse?
The 2 pi FL is the inverse of the capacitor version of it.
Mm-hmm. Because with capacitor and current, their relationship for capacitors, the voltage and current relationship is inversed compared to resistors and with inductors. Because reactance, even for an inductor, is a measurement of the opposition to the sinusoidal current value, its equations for series and parallel are the same as capacitors. So for series, we just add all the reactance values together. In parallel, we add those inverses together. Yes. Mm-hmm.
Is there any sort of thing for the opposite of like a resistor, like the reactance or some sort of?
Reactance always looks like a resistor.
Okay, I was gonna say, I don't know how you calculate total resistance. Calculate the reactance of like a component that's like in parallel with the resistor, but you don't calculate it. I didn't make any sense.
We will come back to resistors in a little bit. We'll see that the reactance for a resistor, so the XR is just equal to R.
Yeah, which makes sense.
So when we go through and we look at RLC circuits, we'll put everything into reactance. And then we're just like, that's cool. Now they're all resistors.
Yeah.
and go through and treat it that way. Yep, that's why we like reactants. Yeah. So Ohm's law looks a little bit different now. It's XL instead of R when we have our inductors this way. Any questions before we go through and try our example? So for this one here, we are determining the current through the inductor 2. So that would be, right, this one here. So I want you to go through and work on figuring out how do you set that up and solve for it. I'll tell you right now, the answer nowhere is 50.
Question.
Yes.
So with resistors, we have our delta or Y. Do we have similar things with capacitors and inductors? Okay.
Not that I'm aware of. Typically, we'll just see them in series or parallel. If you want to go through and convert them, if it's in an AC circuit, you always just put everything in reactance. And then you can go through and use the delta to Y stuff.
Okay. So let's do that. Change. It works real great. Oh, it's fine. Because we work backwards. That. Oh, yeah, because residents is the production of inductance. So it's
I'm gonna give you guys one more minute-ish to go through and finish up what you're working on before we talk about it as a class.
no. It determines the reactants, and then you use those.
Yeah. Final state.
So look at what I use. Okay, wait.
But later on,
Yep.
the city or even.
So let's talk about, before we even think about using math, just from the circuit diagram, what are some pieces of information we know?
L2 and L3 have the same voltage drop.
Okay, so let's just call that, oops. And how do we know that?
Because they're in parallel.
Mm-hmm. So V2 equals V3. Because they are in parallel, the change in voltage has to be the same. What else can we get out of the circuit diagram? What other information can we get out of the circuit diagram?
Obvious things.
Yeah.
L3 is like the current.
Mm-hmm. What else?
The
Frequency.
Mm-hmm.
felt like that was too obvious.
No.
And volt.
The
What is 10? So what does 10 volts here equal?
said leaking easy.
We're not 100% sure. It might be the peak. It probably is, but in this case, we're just going to call it VT. It's the total voltage that is being supplied into the circuit. So that's going to be 10 volts.
Oh, we're not fine.
No, we are not finding the numerical value for L2.
Oh, I thought we were.
We want to find the current through L2.
Oh, just the current.
I mean, we can stop on the way, I guess, if we want, but we don't have to.
So I'm done.
Okay, so we also have L1 and L3 that are given to us. Am I going to want to use L3 and L1 directly? No. How do I want to use them?
We want to get our Excel set up.
Okay. So we'll have XL1 and we'll have XL2. So for both of these, we're going to be going through and using the equation where X is equal to 2 pi F times the L value. Here, my frequency is given in kilohertz and my inductance is given as millihenry. do I need to convert? Why not? Yeah, they're going to cancel out, so I can keep them as they are. So I'll have 2 pi, 3 kilohertz. I'm going to have, for L1, I'll have 5 millihenry, which taking that and plugging it in, I got 94.248 ohms. And I can do the same type of thing for L3. 2 pi, 3 kilohertz, 3 millihenry, 56.549 ohms. Now what? What can I go through to do right? I still want to work towards the goal of finding the current through L3. So what's the next thing I probably want to go through and do?
Probably want to find the voltage drop of L3.
Okay, so how can I do that?
It would be the current times the reactance.
Mm-hmm. So it'll be I3 XL3. In this case, do I want to convert my milliamps?
Yes, you don't have any. You can't put.
Yeah, I don't have anything to cancel it out with. I want to have my value here in volts. So I should go through that step. So I'll have 50 times 10 to the negative 3 amps times my 56.549 ohms. So taking that and plugging it in, I got that my voltage value across 3, which is also across 2, is 2.8274 volts.
Take that number, subtract, and you get your voltage drop across L1,
Mm-hmm.
and that would give you, and then take that and get your current.
Yes, so we're going to now find the voltage drop across 1, because that's going to be VT minus V3. We're going to take our 10 and we are going to subtract out this value. If I'm being honest, I at this point got lazy writing stuff out and I just started rounding things. I kept extra digits for going through and doing my values. I just got lazy in doing my notes part, so apologies for that. But I got, right, this rounds to 7.17 volts. Questions so far? So now that we've found this, we can find the current that's passing through L1. We'll have I1 is equal to V1 over X L1. So this is going to be our 7.17 volts over our 94.248 ohms, which again, I got lazy and started rounding stuff. So 76.1 milliamps. So from here, how can I get I2? Yeah.
Subtract the 50 from the other, from I1, is what it was called, I don't remember, yeah, I3.
Yeah, so all of the current has to pass through inductor 1. 50 milliamps of it is going to go through the right side. That means the remainder of it has to be going through inductor 2 here. So again, right, we have our 76.1 milliamps minus the given 50 milliamps in the circuit. So going through and plugging that in, I got that I2 is equal to 26.1 milliamps. Any questions about 37? Any questions about inductors in DC or AC circuits? All right, so next week we are going to be coming back to both the RC and RL circuits, and we'll be revisiting them again in more detail, figuring about their responses, as well as focusing on the phasor stuff a little bit more. So I will see you on Tuesday.